Hello and welcome back to Project 152. We are up to week 9 and these are going to be the solutions. Now we had a little bit of a layoff for a few weeks. We went through the Easter holidays and things like that. Had a lot of trouble getting back. If you're anything like me, you might be having some trouble. But I'll tell you, once you get started, you'll be fine. So jump in, do the questions, check them out, watch the video. I want to give a shout out to Mr. Harrison's class in particular. I was really procrastinating about making this video, but they sort of jumped in and said, we need this video. So shout out to you, Mr. Harrison. Shout out to the class. Thank you very much for the inspiration. On to the first question. All right, so here we are, equation of a line passing through 2 points. Clever kind of question here because they've expressed it as a vector equation and as a Cartesian equation, and they're kind of testing your ability here to do like one or the other. Okay, now part A and part B, they're vector equations. Now the first part of our vector equation should be one of these points, right? And if I look at 2, 4, 5, yes, that's one of my points. So maybe A is an option here. Now, when I look at B here, negative 3 plus 2j minus k, that's not part B. That's not point B. That's the opposite. That's all negatives. So I'm going to cross that one out. All right, so let's explore A a little more. Now, the second part here, this 3i minus 2j plus k, that's supposed to be the direction that this thing is moving in, right? Now, look at this. 3, negative 2, 1. That's this point. That's not the direction that it's moving in. That's that point. In order to find the direction that it's moving in, you would have to find vector A, B. And that's not what they've done. All right, so it's not a maybe anymore. Option A is out. Which leads us to think that part C and part D, one of those are the answer. Now, on your specialist formula sheet, you will find this. Here is the Cartesian equation. X minus A1, Y minus A2, Z minus A3. So those are all points, A1, A2, and A3. So let's look at each of these. Negative 1, positive 6, positive 4. Neither of our points is 1, 6, 1, negative 6, negative 4, because the signs need to be opposite. That's not it. What about D? X equals negative 3, positive 2, negative 1. Positive 3, negative 2, 1. Yes, those A values are the same, just with signs reversed, which is what we need. So I'm liking those A values for part D. So what are these bottom pieces? Well, look at our formula, D1, D2, D3. That's the direction that it's moving in. And so let's see, negative 1. Okay, this 3 here and this 2, they're 1 apart. So I can do like 3, I can do 2 minus 3. That'll give me negative 1. What about 4 minus minus 2? That'll give me 6. Good. And what about 5 minus 1? That'll give me 4. Great. Fantastic. That is the answer. Option D. Celebrate. Next question. Okay, we've got the equation of a sphere here, right? And we've got it in this weird expanded form. So it feels like we're going to have a little bit of work to do. Now, first of all, we can see that they've shown us where the origin is, and then they've also shown us where the center of the circle is, point A. So the center is 1, 0, negative 1. And then there's this point on the edge, 1, negative 3, negative 5. That's super interesting. Okay, let me remind myself, what is the equation of a sphere? There it is. X minus A squared plus Y minus B squared plus Z minus C squared equals R squared. And so those are my 4 important pieces. A, B, and C are the coordinates of our center right there. So we get X minus, now you got to be careful because it's like the signs, you got to think about that. So X minus 1 squared plus Y. Now that's a 0, so we'll just do Y squared there plus Z, and then that's a negative 1, so it's minus minus 1, so plus 1. Squared equals R squared. Okay, not too bad. We're not told the radius. We've really got a bit of an issue here. They're not telling us anything about the radius. But we have a center, and being careful here, there's my... Alright, so whatever the length of that is, that's my radius. So I should be able to find the distance between 2 points. That's just like Pythagoras in 3 dimensions. But rather than thinking like Pythagoras, let's go sort of a bit more vectory. The thing I've drawn is vector AB. Okay, and vector AB can be calculated as OB minus OA. Now OB is just the point B, so 1, -3, -5, and OA similarly is just 1, 0, -1. Calculating that's super easy, you just need to be careful with all of the signs. Aha, I can see what they've done here, it's quite clever because they've got this -3 and this -4 here. If we want the magnitude of AB, it's just the square root of that squared, -3 squared, plus -4 squared. And you should have seen this a million times by now. That's -3 squared is 9, not -9. -4 squared is 16, not -16. That's root 25, which means that the magnitude of that vector is 5, which means that the radius of our sphere is 5. Let's replace that r now with 5. All right, now, annoyingly, we've still got to expand everything because it's in expanded form, not in this nice little factorized form. So x minus 1 squared is the same as x squared minus 2x plus 1. Y squared is just y squared. And z plus 1 squared is z squared plus 2z plus 1. And, of course, 5 squared is 25. Okay, the positive one here, the positive one here, we can group that with 25. And so that's going to give us our 23. Not overly, that narrows it down to a and b. And what am I left with here? I'm left with x squared minus 2x plus y squared plus z squared plus 2z. Okay, let's take a look. X squared minus 2x plus y squared plus z squared plus 2z equals 23. Yes, correct. The answer is A. A little bit of work there, a little bit of thinking. It's just not given in the form that you're used to. I've not often seen this where you've got the center and like a point on the sphere. But finding that radius is pretty straightforward, and then expanding also pretty straightforward. Done. So I've been very particular about choosing this question for this time of the year. This is Unit 4 work, but if you haven't yet started Unit 4, which I know some of you can still answer this question just with what you know from maths methods, right? The problem is that a maths methods student doesn't know how to integrate this. But the good news is that a maths methods student knows how to derive these. And because integrals and derivatives are the opposites of each other, a way to solve this, if you don't know how to do it using specialist work, is just to derive all of these and see which one of them gets you to this answer. Integrals, derivatives, reverses of each other. But for the purposes of this video, I am going to assume that you have started doing Unit 4 work, you have learned how to integrate using substitution, and that's what I'm going to do. I'm going to integrate using substitution. Alright, so how do I know that I need to integrate using substitution, or that I can integrate using substitution? I've got this 4x here, right? And then it's being multiplied by 3x squared plus 5. All right, and they're related to each other. 4x and 3x squared plus 5. 4x is a derivative of 3x squared plus 5. And when I say it's a derivative, I mean it's a multiple of a derivative. It's not the exact derivative, but x and x squared are derivatives of each other. Okay, so now that I know that, whichever one is the higher power, so 3x squared plus 5, I'm going to take that, I'm going to let it equal u. Okay, so now that I've let 3x squared plus 5 equal u, I can find the derivative of u with respect to x. The derivative of u with respect to x. And that's just going to be 6x. And then I can do this neat little thing, and I can say, and therefore, dx equals du on 6x. Okay, so this fancy little thing. Now that I've done that, that gives me enough to be able to sub it all into here and some magic happens. So, integral 4x, and then replacing 3x squared plus 5 with u times u. Now it's being raised to the power of 3. This seems really wild, but then it all cleans itself up at the end. And then we have this du on 6x. Okay, so what happens here? the x and this x here, they can cancel each other out, top and bottom, right? And so now we've also got this 4 and this 6, and they can cancel each other out as well as 2 and 3. 2 and 3. All right, so bringing this all together now, we get equals the integral of 2 u to the 3 divided by 3 with respect to u. Magic. Now, we know how to integrate something like this. Increase the power by 1, u to the power of 4. Divide by the new power, so 3 multiplied by 4, because I'm bringing this 4 down here to the 3. So over 12. I've got that 2 there. And then I'm going to need a plus c. Okay, it's pretty much done now. 2 over 12 is the same as 1 over 6. And u is not u. U is 3x squared plus 5. And I've still got my plus c. Okay, are one of these the answer? Option A. Done. Now, of course, like I said, if you wanted to, you could just go through all 4 of these options, derive them, and you should end up there for part A. So that could have been an easy way of going about it, but this is integration by substitution. Celebrate, and we've got a couple of short response questions to go. All right, so we've got some complex number style stuff going on here. The vertices of a regular hexagon are positioned on the circumference of a unit circle, which means it's a radius of 1, as shown on the Argand diagram. Just drawn in my little 1 and my 1 here. There's like a -1 there and a -1 there. Okay, determine W, expressing your answer in the form r cis theta. All right, and it's, if I just move over here a little bit, there's only 1 mark for it, so we just need to be able to do it, right? Shouldn't take long at all. All right, so where's W? W is right here, and we're trying to express it as W equals r cis theta. Okay, r is the modulus. It's the length here between the center and W. It's a unit circle, right? And it's sitting on the circumference of the unit circle, so that length must just be 1. We won't need the 1, but we'll just write it down for now. So from here, we've got to think about the angle. Now, this is a hexagon, so we're dividing a circle into 6 equal parts. So 360 degrees in a circle, or 2 pi radians in a circle, however we want to work there. Now, 1 is going to be 60 degrees. That's going to be 120 degrees. But I'm going to work in radians. 120 degrees is 2 pi on 3 radians. Don't need that extra equal sign. Oh, yes, I do. This 1's a bit nonsense, right? So let's just go cis 2 pi on 3. That's my answer. Okay, so part B says we need to convert our answer into Cartesian form. So W equals, a lot of people get confused here, but this cis, what it stands for is C cos of the angle 2 pi on 3 plus sine of the angle 2 pi on 3 I. That's what cis is. If you didn't realise that until right now, now you know. The formula for converting from polar form to Cartesian form is sitting within this little thing right there. And then you just need to know what the value of cos 2 pi on 3 and sine 2 pi on 3 is. Now, I like to use a standard triangle for this. Cos pi on 3 is equal to adjacent over hypotenuse, 1/2, but we're in the second quadrant. So cos is going to be negative, plus sine 2 pi on 3, so sine pi on 3 is equal to opposite over hypotenuse, root 3 on 2. And we're in the second quadrant, and it's going to be positive I. Do a little double check. We're in the second quadrant, we're over here. It makes sense that we would have a negative real component, and it makes sense that we would have a positive I component. I'm happy with that. There's my answer. Okay, so what's the next part of it? It says, each vertex of the hexagon is a solution of an equation z to the n equals a. All right, z to the n equals a. And then it just says state the value of n. We have 6 points equally spaced around a circle, z to the n equals a, n must be equal to 6 because we're getting 6 solutions. So we just say n is equal to 6. Okay, that's C. Part D says state the value of a. Well, we're told this is a unit circle, right? And so in particular, for this kind of equation, when we're doing roots of complex numbers, what we're dealing with here is what's called a root of unity, or the 6 roots of unity. And that's just the solution to z to the 6 equals 1. So we can say that a equals 1. Not a whole lot of working here. You're just supposed to know about this thing called the roots of unity, and this should just like pop out to you. Now, if this value was different, if it wasn't 1, if it was like 8 or something like that, we'd have to do some more work. We'd have to like raise 8 to a power to figure out where we come from. But for this, it's a root of unity. It's on a unit circle. You're just supposed to know, and the QCAA loves to test your ability to know stuff about the roots of unity. So it's something you're supposed to know. All right, final part. Verify that W satisfies the equation Z to the N equals A using your results from C and D. So we need to use this fact. We need to use the fact that Z to the 6 equals 1 is our equation. And we need to show that W, what we know about W, which is W is equal to this, we need to use this, we need to verify that this actually fits into this equation. So let's see if it fits into this equation. So left-hand side equals z to the 6, and the right-hand side is equal to 1. Now what's z? Now I'm verifying that this works. So let's see. Cis 2 pi on 3, and I'm raising it to the 6. All right, so we're using like de Moivre's theorem here, however you want to pronounce it. There's a 1, like an invisible 1 sitting here that we got rid of earlier. 1 to the power of 6 is just 1. So that stays just as a 1. And then if we want to raise this to the power of 6, we multiply it by 6. That's de Moivre's theorem. So we end up with cis 12 pi on 3. All right, we don't need the 1. Sorry, I'm sort of ending up sort of working through my work, but hopefully you can follow me here. Cis 12 pi on 3, that's equal to cis 4 pi. Now, cis 4 pi, what's 4 pi? That's 2 rotations of a circle, which means we end up back here again. So we can simplify this as either cis 0 or cis 2 pi, however you want to look at it. But what is the value of cis 0? The value of cis 0 is 1. Just a real value right here. Right here. 1. So we can now confirm that the left-hand side equals the right-hand side. We have verified that solution. Okay, bit of a question here. It is a question, even though it's a question 11, it is a question that students do have a little bit of trouble with because they don't spend a lot of time thinking about the roots of unity and thinking about what it means when you find the nth root of a complex number in terms of a picture. So this question really combines the idea that, hey, it's a picture. You can draw it with some algebraic stuff. Celebrate, and one last question. All right, here we go. Last question. It's a complex number question, and it's a proof. So you should remember doing some direct proof stuff in Year 11. I know because I'm teaching my Year 11's direct proof right now. It comes in handy here. So I'm going to make a bit of a show of making sure that I set this up in a very pretty kind of a way. So first step, I'm going to write RTP, which stands for required to prove. So it is required to prove that this is equal to this. And now that I've set that up, I'm going to split up my left-hand side and my right-hand side. Really important step for a direct proof. All right, hopefully you get a sense that I haven't actually thought about too much yet. I've just kind of said, well, I know what I need to do. I need to prove this. So it's required to prove. And I know that it's an equation with an equal sign, left-hand side, right-hand side, so I'll split those up. I reckon I'm probably going to get a mark even before I've just started, so not bad. What next? Well, I'm told that I need to use A plus BI for Z, and I need to use C plus DI for W. So just everywhere on both sides, I'm going to replace z with a plus bi, and I'm going to replace w with c plus di. Alright, I'm nearly finished. I just got a little bit more to do, but I'm going to do that while I talk to you. Now this bit here, a plus bi, that's z, minus all of w, right? There's a tendency for people not to put some brackets there, but you really need them because you're subtracting the c and you're subtracting the di. Those vertical lines, the magnitude of whatever that happens to be, squared. Okay, and then here we have the magnitude of z squared plus the magnitude of w squared minus 2 times the real component of a plus bi times, and then this little line above the w means the conjugate of w. So instead of putting c plus di here, I'm going to be putting c minus di here. Alright, so I'm going to do my proof in order of how easy it feels. So here I see that this, I'm finding the magnitude or the modulus of a complex number, and then I'm going to square it. Alright, so to find that, it's the square root of the real component squared plus the imaginary component squared. Not with the I, right? Because we're just finding the magnitude of our complex number. Now the thing that I've just drawn is from here to here, but then at the end I need to square it. Quite odd, right? Because I'm square rooting it here, but then I'm squaring it again. So actually the square root and the squared are going to cancel each other out. So I'm just going to end up there with a squared plus b squared. Square root, square, cancel each other out. Alright, here we've got the same deal. We've got c squared plus d squared, the square root of that squared, which is just going to be c squared plus d squared. Okay, what have we got here? Minus 2 times the real component of this. Now I'm going to expand that because it's going to be a times c. And then I'm going to end up with a times negative di, so negative a di. And then I'm going to end up with this bit, which is plus bci. And then this last bit is maybe the weird bit. bi times negative di. That's going to be negative b di squared. But we know that I squared is negative 1. So negative bd times negative 1 is going to be positive bd. Okay, what does all of that mean? Well, this is going to be 2 times the real component of this. This is not a real component. This is an imaginary component. This is not a real component. This is an imaginary component. So the real component of all of this, with the bracket there, is this and this, right? Yeah, because that is real. It's positive BD because the I squared is negative 1. So how am I going to show that? 2 times the real component, and the real component is just AC plus BD. Okay. Is there much more I can do here? I have an A squared, I have a B squared, I have a C squared, I have a D squared, and then I have this bit of stuff going on here. I don't know. Maybe I should expand that and be like negative 2AC, negative 2BD. But I feel like now that I've done all this, I can just leave it for a second, go over here, see how that feels, and like maybe I'll start to get a sense of what's going on. So here, we're being told again to find the magnitude of this complex number. I think maybe I'll just step it through, because this complex number has these real components, right? This A and this negative C. A minus C. Now, I don't know what they are. A could be 7 and C could be 11, but they're all complex numbers. So we just got to leave it as A minus C. And then we have this plus B minus D I. What have I done there? Well, it's plus BI minus DI, right? And if we try to group those two imaginary components, we just add their coefficients together. In this case, B minus D. And then the magnitude of that, and then we're going to square that. All right. How do you find the magnitude of a complex number? You take the square root of the real components squared plus the imaginary components squared. And then we're trying to square it at the end, right? Magnitude squared. Okay, so that means that that square root and that squared are going to cancel each other out. And I'm left with a minus c squared plus b minus d squared. Where does that take me? And this is sort of a rule for when you like sort of glance over here, look over here, ask yourself, am I there yet? And does it feel like there's a place I'm going? As a general rule, when you're doing like direct proofs, just expand, expand, expand is often a very easy and simple way to go. If you expand, 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 you can end up just, oh, doesn't always work, but that's kind of the vibe that I'm going for today. Okay, a squared, this is going to be minus 2ac plus c squared. Similarly, we're going to end up with b squared minus 2bd plus d squared. And again, you're glancing back and forth, right? What do I see here? Well, I see it looks very similar to this because I see like an a squared, I see a b squared, I see a c squared, I see a d squared, and then I see this funky little pieces left over. Negative 2ac, negative 2bd. Now, how you choose to proceed from here is totally up to you. You could like factorize this to make it look like this, or you could expand this to make it look like this. But I'm going to expand because that's what I was talking about earlier. Just expand, 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 and hope you end up with the right answer. 2ac minus 2bd. Okay, I think I've got it. Duh, that looks the same, that looks the same. And then I can just say that the left-hand side, equals the right-hand side. That's probably the best way to go. This is the left-hand side, this is the right-hand side. You can now see that the left-hand side does indeed equal the right-hand side. I like to give it a little tick. I like to write a little QED, quadrat demonstratum, but totally unnecessary. Just a bit of a flex at the end. And that is proven. And those are our week 9 solutions. Now, as I said at the start of this video, had to sort of blow the cobwebs out. I was feeling a little bit tired. You probably saw it in the video, but we've pushed through. We've gotten our answers done. Next week is a new week. Speaking of next week, I have included a couple of Unit 4 questions, but because it is a tech active week, this question is going to be one of them, and you'll be able to do it just using your calculator, even if you've done no Unit 4, just using your methods knowledge and your calculator. Similarly, I've also included this question, which again, you will be able to do using your calculator knowledge and what you know about stuff in methods. So don't panic, you'll be able to do these questions regardless of where you're up to. We're going to start sprinkling in more Unit 4 stuff as time goes on, but I just wanted to give you the heads up. Don't throw it away thinking you haven't done it. You can do it. Catch you next week. Link to the questions in the description below. See ya!